We owe the concept of correlation and the concept of regression to Francis Galton. But the formalization of the correlation coefficient was done by Carl Pearson, who was a mentee of Galton, and he was his biographer as well. The concept of the correlation coefficient, in a sense, is very simple. It is just one value that gives information about the strength of the relationship between two variables. And also the sign of that number indicates the direction of the relationship. So the values of R go from -1 to 1. 0 indicates that the two variables are not associated at all. -1 indicates that they have a perfect negative association, and +1 is that there is a perfect positive association. Values between -1 and 0 indicate that there is a negative association, and the closer the value to 1, the stronger the association, the closer to 0, the weaker the association. Likewise, values between 0 and 1 indicate a positive association. The closer to 1, the stronger the association, the closer to 0, the weaker the association. Negative and positive indicate how the two variables vary together. In the case of negative correlation, it indicates that if the values of one variable go up, the variables of the other variable go down. And positive values, if the values of one variable go up, the values of the other variable also go up. But in another sense, the concept of the correlation coefficient is complex because it has two components, and we need to understand both components, not just one of them, to understand fully the concept of correlation coefficient. One is the variability of the data that is accounted for by the regression model. And the second one is the slope of the regression line. As you can see, the regression and correlation are intimately related. Let's consider the variability of the data accounted for, and that is a statistic called R-square. In this case, we've got 30 values represented by the orange dots, and in a variable y that takes values from 0 to 100. The mean of those 30 observations is 50, and is represented by the green line and by the y bar. Now, in this case, all the values are 50. Let's consider another situation in which the values of this variable are different, but the mean is also 50. Now, we can see here that the values were at the beginning all at the mean, and now there is a variability. So the values are spread, dispersed from the mean, values higher than the mean and values lower than the mean. We can refer to that as the total variability of the data. In this case, the data is the values in variable y. And we can have a number of ways of providing information about the variability of y. In the previous case, in which all the values were exactly the value of the mean, the variability is 0 because all the values were at the mean. We can have three measures, or three main measures of the variability of the data. One of them is called sum of squares. And the sum of squares is a sum. The Greek letter sigma indicates sum. And what it sums, the sum of squares, is the squares of the difference between each value, each orange dot, and the mean, represented by y bar. So we've got sigma that goes I equals 1 to n. The letter I is an index that provides us with a shortcut. Instead of putting y1, which is the one value, y2 the second value, y3 the third value, and we have to annotate the 30 values that we have in this data set, we put y sub I, and that is a shortcut for all the possible values of y, and we indicate that those values go from 1 to n. In this case, n is 30. So basically, this means that we are going to have 30. So this equation is a shortcut for 30 times y. So we've got, in all these cases, for each value of y, we are going to subtract the mean, represented by the y bar in the formula. Now, if we just do that, we subtract the mean from each of the values of y, we are going to have negative numbers and positive numbers. What happens if we add all these numbers? Well, the sum of these numbers will be exactly 0. It doesn't matter how dispersed or how close to the mean the values are, the sum of those values will always be 0. So we need a way, an operation that allows us to get rid of the sign. So we've got an absolute measure of the distance between the observations and the mean. And a way of doing that is obtaining the square of those values. Because when we square two positive values, we get a positive value, and when we square a negative value, we obtain a positive value. So by squaring those differences of the values from the mean, we obtain all positive values. And when we sum that, it won't be 0. And it will give us an idea of the distance from the mean. The higher the sum of squares, the higher the distance from the mean. Now, we've got a problem with that measure. This measure is very useful in some situations, and we are going to see the usefulness of that later. But in other situations, it's not informative because it depends on the number of observations. The more observations we have, the larger the sum of squares. But perhaps we may have a lot of observations that are very close to the mean, but because we have a lot of observations, the sum of squares will be a large number. So what we can do is to obtain an average of the differences of the sum of squares. And the way we do that is by observing the variance formula, which obtains the sum of squares, and then all those values are divided by n minus 1. So in this case would be divided by 29. So we know that the average, that in order to calculate the mean, we obtain an average, and we divide by the number of observations by n. Why do we divide by n minus 1 in this case? Well, it has to do with using the variance in the sample to estimate the variance in the population. It turns out, statisticians found out, that if we divide by n-1, we get a better estimation of the variance of the population. It's just because of that. Okay, so the variance is a very useful measure of the variability of the data. Now, when we calculate the sum of squares, remember that we square all the values. So that variance will not give us it gives us a useful information, but it's not related to the variable, because we square those values. So one way to make make the variance to indicate an average distance from the mean is to obtaining the square root of that value, and the square root of the variance is what we call the standard deviation. And so if we have a standard deviation of 5, that indicates that the average distance from the mean is 5.